Welcome to Chapter 16 on autoencoders and representation learning. In this chapter, we explore a neural network whose only job is to copy its input and why that simple idea turns out to be surprisingly powerful. Here is a puzzle that sounds pointless at first. Build a network whose only task is to copy its input to its output. Autoencoders matter because they sit at the crossroads of several big ideas, and we will build them from the inside out. By the end of this chapter, you should be able to explain the purpose of an autoencoder, describe the encoder, bottleneck, and decoder, define reconstruction loss, and explain how autoencoders perform representation learning. You should also be able to compare autoencoders with PCA, explain denoising autoencoders and why corruption helps, describe sparse autoencoders, and see how reconstruction error supports anomaly detection. This figure shows the big picture. An autoencoder compresses the input into a compact latent vector at the bottleneck, then reconstructs the original. Training minimizes reconstruction error, and a high error on a new input signals something unusual. So, what is an autoencoder? It is a network trained to reconstruct its own input, made of an encoder that compresses, a bottleneck that holds the compressed form, and a decoder that rebuilds it. The narrow bottleneck forces the network to learn structure rather than memorize. The key to the whole idea is the constraint in the middle. The encoder compresses the input, the bottleneck holds its distilled essence, and the decoder rebuilds the original. A well-designed autoencoder simply cannot cheat by memorizing. An autoencoder has three parts, and it helps to look at each one in turn. The encoder is the compression half of the network, mapping the input into a smaller code. That code goes by several names: the latent representation, the latent code, or simply the encoding. The bottleneck is the narrowest layer, sitting between the encoder and the decoder. It is the squeeze point that forces the network to keep only what matters. The decoder is the mirror image of the encoder, rebuilding the input from the compressed code. The aim is for the reconstruction to come as close as possible to the original. This figure pictures the autoencoder as a symmetric hourglass. The encoder narrows the input down to a compact latent code, and the decoder widens it back out to a reconstruction. An autoencoder learns by minimizing reconstruction loss, which measures how far the reconstruction strays from the original input. For continuous data, the usual choice is mean-squared error, and for binary data or pixels scaled between 0 and 1, binary cross-entropy is common. The real value of an autoencoder is rarely the reconstruction itself, since we already have the input. It comes from the byproducts: dimensionality reduction, feature learning that feeds other models, data compression, and denoising of corrupted inputs. There is more: anomaly detection that flags inputs which do not fit, pre-training that gives another network a head start, and generative modeling in the variational form. The common thread is learning from unlabeled data. The most direct use of an autoencoder is dimensionality reduction, shrinking high-dimensional data down to a compact, manageable representation. Let us compare PCA with autoencoders. PCA finds linear directions, while an autoencoder can capture nonlinear structure that a purely linear method would miss. An undercomplete autoencoder is the standard kind. Its bottleneck has fewer dimensions than the input, and that squeeze is what forces useful learning. But what if the hidden representation is as large as the input, or even larger? Then we need a constraint that makes lazy copying impossible, even when capacity is plentiful. A sparse autoencoder adds a penalty that pushes most hidden neurons to stay inactive for any given input. The loss gains an extra sparsity term that grows whenever too many neurons fire at once. A denoising autoencoder is trained on a deliberately harder task: reconstruct the clean input from a corrupted version of it. The recipe is simple: Start with clean data, add random noise to the input, feed the noisy version through the encoder, and train the decoder to reproduce the original clean input. Because the network sees noisy inputs but is graded against clean targets, it cannot succeed by copying. It must learn the underlying structure well enough to fill in what the noise destroyed. Denoising autoencoders are used to remove noise from images and signals, to learn robust noise-tolerant representations, to pre-process data before another model consumes it, and to improve generalization. One of the most practical uses of autoencoders is finding the unusual, and the mechanism is beautifully simple. Train on normal data, then feed it something anomalous, an input unlike anything it saw in training. The applications span industries. In manufacturing, unusual sensor readings may foreshadow equipment failure. In finance, an out-of-pattern transaction may signal fraud. In cybersecurity, anomalous traffic may mark an intrusion. And in healthcare, unusual measurements may flag a developing risk. The approach is powerful, but it demands care in how we use it. The anomaly detection idea is easy to state, but easier to trust once we push a couple of numbers through a real, if tiny, autoencoder. Imagine a machine watched by two standardized sensors, one for temperature and one for vibration. This equation gives the reconstruction error for our tiny network. It works out to the squared difference between the two sensor readings, divided by 2. Notice that the error depends only on one thing: how far the reading sits off the diagonal where the two sensors agree. Take a normal reading where the two sensors roughly agree, say temperature 3 and vibration 4. Because they are close, the reconstruction error stays tiny. Now suppose a fault drives vibration far above temperature, giving a reading of 2 and 8. The two sensors now disagree sharply, and the error will jump. This table collects the reconstruction errors for 4 normal readings and 1 anomaly. A threshold placed anywhere between about 1 and 17 cleanly separates them. The table makes the separation stark. The normal readings all reconstruct with error at most 1/2, while the fault jumps all the way up to 18. This figure shows anomaly detection by reconstruction error. The autoencoder learned the gray diagonal where normal readings lie, so normal points reconstruct onto the line with almost no error, while the anomaly sits far off it. This tiny network is linear, so it behaves just like projecting onto the first principal component from Chapter 13. That connection is no coincidence. A variational autoencoder, or VAE, is a more advanced cousin, built specifically for generation rather than just reconstruction. Here is the contrast. Standard autoencoders learn a compressed representation. Variational autoencoders learn a probabilistic latent space, and that lets VAEs generate genuinely new data samples. VAEs place autoencoders firmly in the lineage of generative modeling. A latent space is a compressed representation space the model learns, where each point corresponds to a possible output and similar inputs land near one another. Autoencoders bring real strengths. They learn from unlabeled data, reduce dimensionality in nonlinear ways PCA cannot, denoise and learn robust representations, detect anomalies through reconstruction error, and introduce the latent space ideas behind generative AI. They also have clear limits. They can demand a lot of data and careful tuning. Their representations can be hard to interpret. Good reconstruction does not guarantee useful features. Thresholds are tricky to set, and an overly powerful model can simply memorize. Here is the key point. Judge an autoencoder by the goal, not by the reconstruction. A model can reconstruct almost perfectly, yet still produce useless features or miss the anomalies you care about. Always validate against the real objective. Now let us build an autoencoder in Python and watch it compress images. This code loads the fashion MNIST images, ignoring the labels since autoencoders are unsupervised, scales the pixels and flattens each image, then defines an encoder that squeezes each image down to a 32-dimensional code, with a decoder mirroring it back out. What this autoencoder does is compress every 28 by 28 image into a 32-dimensional code and then reconstruct it, which is roughly a 24-fold compression. Numbers in a loss function are abstract. Seeing the reconstruction side by side makes the compression tangible. This code plots two rows of images, the originals on top and the reconstructions below, so we can compare them directly and judge the quality with our own eyes. The top row holds the originals, and the bottom row holds the reconstructions rebuilt from a mere 32 numbers each. Often, the reconstruction is just a means to an end. What we really want is the compressed representation itself. This code builds a smaller model that outputs only the bottleneck code, then runs the test images through it to produce their compressed encodings. The encoded array has just 32 columns instead of 784, a dramatic reduction while keeping the essential information. Finally, let us turn the same autoencoder into an anomaly detector. This code computes the reconstruction error for every test image, then flags the worst reconstructed 5% as anomalies by setting the threshold at the 95th percentile of those errors. Here we simply call the top 5% of errors anomalous, but in a real system that threshold is a deliberate decision, not a default to accept blindly. Consider a factory running pumps and motors, each streaming temperature, vibration, pressure, and current every few seconds. Failures are rare, so the company has mountains of normal data and only a handful of labeled failures, yet it wants early warning before a machine breaks down. This is a textbook fit for an autoencoder because of the data itself. The workflow follows the anomaly detection recipe. Collect plenty of normal operating data, clean and scale the features, and train an autoencoder to reconstruct the normal data. Then compute reconstruction errors on live readings, set a threshold using validation data and engineering judgment, and route high error cases to engineers. As a machine starts to fail, its signature drifts and the error climbs, though the earlier cautions still apply. The following code demonstrates this anomaly detection workflow using en2 handwritten digits, training only on the digit 0 and flagging every other digit as an anomaly. This code keeps only the digit 0 images as the normal class, builds an autoencoder, trains it solely on those normal samples, and then scores every test image by its mean reconstruction error. Inputs from unseen digit classes produce higher reconstruction error than the normal digit 0 distribution, so the threshold cleanly separates normal from anomalous inputs. An autoencoder is a network trained to reconstruct its own input, and its quiet brilliance lies in the bottleneck. We met a family of variants, each shaped by a constraint, and in Python we built one, visualized its reconstructions, pulled out its representation, and made it an anomaly detector. For further reading, look to introductory deep learning textbooks on autoencoders and representation learning, the TensorFlow and Keras documentation and tutorials, applied guides on anomaly detection, and accessible introductions to variational autoencoders. Two landmark works are worth knowing. The original variational autoencoder paper introduced the probabilistic latent space framework, and the generative adversarial networks paper offered an influential alternative that shares the same latent space ideas. That brings us to the end of chapter 16 on autoencoders and representation learning.